Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back to the show. We have a fascinating paper on the desk today, and it's one that I've really been itching to discuss because it messes with a lot of the mental furniture I've arranged about how the early universe works.
Oh, this one. Yes. The Texas A&M paper from Nature Astronomy. This is a big one.
It really is. The headline is, catchy, something about a cosmic car crash, which is great. But the actual data, I think, it's far more disruptive than even that lets on.
I agree. We're looking at a structure confirmed at redshift 6.71.
Which is deep.
That is very, very deep into the history of the cosmos.
Exactly. For anyone listening, we're talking about a time just 800 million years after the Big Bang. The universe is, about 6% of its current age?
Barely an infant.
Right. And usually when we talk about this specific era, the epoch of reionization, sort of the tail end of the cosmic dawn, we have this standard picture in our heads.
The hierarchical model.
Yes, the hierarchical model. We picture these small, irregular, low metallicity proto-galaxies. We picture them pretty much isolated, struggling to pull in gas, maybe lighting up a few of those first-generation stars. It's supposed to be a structurally quiet time.
It's a bottom-up process, or that's what we thought. You start with small dark matter halos, and they merge, but slowly. You get slightly bigger halos, gas falls in, it cools, and you form these little galaxies. Slow and steady is, or was, the operative phrase.
But this new data from the James Webb Space Telescope, specifically from the JADE survey, seems to have found something that, it just completely defies that slow and steady pacing.
It's not a lonely proto-galaxy. Not even close.
It's a compact group of 5 galaxies all tangled up together. They're calling it JWST's Quintet.
Which is a lovely nod, of course, to Stephen's Quintet.
A very famous local group of colliding galaxies, yeah. But finding something like that today in our cosmic backyard, that's normal. That makes sense. Finding a structure that complex involving 5 distinct galaxies just 800 million years after the starting gun.
That's the anomaly. That's what has everyone buzzing.
So today, our mission is to really take this paper apart. I want to understand, the instrument, the spectral analysis that confirmed this wasn't just some kind of projection effect. And most importantly, what are the physical implications for things like galaxy quenching and metal enrichment? Because this isn't just a, wow, look at the pretty picture story.
No, this is our simulations might need a patch story.
I thought you might say that.
I think that's a fair assessment. It definitely forces us to recalibrate the timeline for how quickly the universe got heavy, chemically speaking, and just how quickly it could build these massive structures.
So let's start at the beginning, the detection itself. Because in astronomy, you're only as good as your signal-to-noise ratio, right?
Always.
This comes from the JADES survey. That's the JWST Advanced Deep Extragalactic Survey. Now, I know the history of these deep fields. We had the Hubble Deep Field, the Ultra Deep Field.
The Extreme Deep Field.
Right. And the basic idea is you point your telescope at a patch of sky that looks completely black, a tiny spot the size of a grain of sand held at arm's length, and you just stare for hundreds and hundreds of hours.
You just let the photons trickle in, one by one. And JADES is the spiritual successor to all of that, but it's using the specific powers of Webb. And the key difference here isn't just, raw sensitivity, although that's part of it. It's the spectral coverage. Webb is an infrared machine.
Which is an absolute prerequisite for looking at this era of the universe.
It is non-negotiable. It's the whole ball game.
Why? Why is infrared so important here?
Well, it's all about the expansion of the universe. At a redshift of 6.7, the light that these young, hot stars are putting out, the really powerful ultraviolet light, things like the Lyman alpha line, that light has been traveling for over 13 billion years. And over that time, the universe itself has stretched.
So it stretches the wavelength of the light along with it.
Exactly.
Yeah.
The UV light gets stretched all the way across the visible spectrum and deep into the infrared. Hubble could see the very, very beginning of this, but it really struggled to get the detailed spectroscopy you need to confirm distances and find out what these things are made of.
So Webb's instruments, the near-infrared camera and the near-infrared spectrograph, they are literally built for this.
This is their prime directive.
So the lead researchers, Dr. Wida Hugh and Professor Casey Popovich, they're sifting through this JDS data. What are they looking for typically? Just a single red dot?
Usually, yeah. The classic technique is looking for dropouts.
Okay, what's a dropout?
You look for a galaxy that appears in your longer wavelength filters, your redder filters, but then it just disappears in the shorter, bluer ones.
Why does it disappear?
Because the neutral hydrogen gas that filled the early universe acts like a thick fog. It absorbs pretty much all the light bluer than a specific wavelength, the Lyman break.
So if it's there in one picture but gone in the next, you know it's really far away.
That's the classic sign. But here, they weren't just looking for a single dot. They found a complex morphology.
A smudge that turned out to be a crowd.
A smudge that turned out to be a crowd. That's a great way to put it. In the imaging, it resolved into 5 distinct clumps of light. They labeled them ELG1 through ELG5.
Yeah.
ELG stands for Emission Line Galaxy.
Let's pause on that emission line galaxy, because that term tells us something really important about the physical state of these objects, right? We aren't just seeing the faint continuous glow from a bunch of old stars.
No, not at all. Emission lines are the fingerprint of violent active star formation.
How so?
When you have a burst of star formation, you create these huge, incredibly hot, short-lived stars. We call them O and B type stars.
Yeah.
And they pump out enormous amounts of hard ultraviolet radiation.
Okay.
That radiation slams into the surrounding clouds of hydrogen and oxygen gas, and it ionizes them. It rips the electrons off the atoms. But then, when those electrons recombine or they cascade back down to lower energy levels, they have to release that energy. And they do it by emitting light, but only at very specific, discrete wavelengths. It's like a cosmic neon sign.
So seeing strong emission lines, in this case, I'd imagine it's things like doubly ionized oxygen, the OI day line. That's basically a giant sign flashing, we are making stars right now.
It's a sign that the party is in full swing, a very, very loud party.
And the fact that they could spectroscopically separate 5 distinct sources, all with compatible redshifts, that's the real smoking gun here.
That's everything. Because if these were just random galaxies at different distances that happen to line up in the sky.
A chance alignment.
A chance alignment, exactly. Then they're redshifts. They're coordinates in time, essentially. They would be all over the place. One might be a redshift 2, another at 4, another is 7. But these 5 all cluster tightly around z equals 6.71. They are true neighbors. They are physically associated.
Okay, so we've established these 5 galaxies are neighbors. But neighbor is a very relative term in cosmology. I mean, Andromeda is our galactic neighbor, but it's 2.5 million light years away. If we collide, it's not for another 4 billion years or so.
A very fair point.
What kind of spatial separation are we dealing with in this quintet? How close are they, really?
It is extremely compact. I mean, shockingly so. The projected separation that we see on the sky implies that all 5 of these galaxies are contained within a region that's only about the size of the Milky Way.
Wait, all 5 of them inside a region the size of our single galaxy?
All 5 of them, yeah.
So let me picture this. You take the Milky Way, which is about 100,000 light years across, but instead of our one big organized spiral disk, you have 5 distinct chaotic blobs of gas and stars all swarming and crashing around inside that same volume of space.
That is exactly the picture you should have in your head. And that density, that proximity is critical. Because at that closeness, gravity is completely dominant. You cannot have 5 galaxies that close to each other without intense dynamical friction. They're constantly dragging on each other. They're stripping material from one another. This isn't some stable, long-term configuration.
No.
This is a snapshot of a collapse. It's a system in the middle of a violent merger.
It's a train wreck in progress.
A 5 train wreck.
Wow. Okay, so this brings us to the energetics of the situation. You mentioned the emission lines tell us that there's a lot of star formation happening. I have to assume that when you mash 5 gas-rich galaxies together like this, the star formation rate, the SFR, just goes through the roof.
It creates what we call a starburst. It's a phenomenon we see in local mergers, too. The antenna galaxies are the classic example.
Right.
When galaxies collide, the gas clouds don't just pass through each other like ghosts. The stars mostly do, but the gas doesn't. The gas clouds slam into each other. You get these massive shock waves that propagate through the interstellar medium.
And what do the shock waves do?
They compress the gas. They dramatically increase its density, which allows it to overcome its own internal pressure and start collapsing under its own gravity.
The gene's instability.
Precisely. You drop the gas below the gene's mass for a given temperature and density, and boom, you trigger a wave of star formation.
And now you're multiplying that effect by 5 interacting bodies.
It's a chain reaction. The researchers on this paper, they calculated the total SFR for this entire system, and the number is it's staggering.
Yeah.
This quintet is producing new stars at a rate of roughly 250 solar masses per year.
250. Okay, let's put that in context for everyone. The Milky Way, our home galaxy, is a pretty big, mature spiral galaxy. What's our current rate?
We're pretty quiescent. We're settled down. We churn out maybe 1 or 2 solar masses worth of new stars per year on a good year.
1 or 2. So this system, just 800 million years after the Big Bang, is over 100 times more active, maybe 200 times more active than the modern Milky Way.
Yes. It is a star factory running at 2,000% capacity.
Mm-hmm.
If the Milky Way is a slow-cooking stew on the back burner, this thing is a flash fryer on full blast.
That's a great analogy.
And that intensity, that's what explains why it's so incredibly bright in the infrared and why those mission lines are just screaming at us. It is burning through its fuel supply at an absolutely breakneck pace.
And that touches on a paradox I really want to explore in a bit, this idea of running out of fuel. It seems counterintuitive. But before we get there, I want to talk about the stuff between the galaxies, because the paper mentions something that I found really visually evocative.
Mm-hmm.
They didn't just see the 5 bright clumps of the galaxies themselves. They saw a halo.
The diffuse emission, yes.
Yeah.
This is one of the most significant findings of the whole study.
So there's this glowing gas connecting them. And it wasn't just hydrogen, was it?
No, that's the kicker. It was enriched. Their spectroscopy revealed the clear presence of ionized oxygen in this extended halo, this bridge of gas connecting the galaxies.
Okay, let's go back to high school chemistry for a second. And stellar nucleosynthesis. The Big Bang gives us hydrogen, helium, and a tiny, tiny pinch of lithium. That's it, full stop.
Correct. The primordial soup is what we call metal-free. In astronomy, a metal is anything heavier than helium.
So oxygen, atomic number 8, it just doesn't exist in the universe until a star makes it.
Right. Oxygen is synthesized deep in the cores of massive stars. It's done through helium fusion. The triple alpha process gets you to carbon, and then capturing another helium nucleus gets you to oxygen.
Okay, so the star is the factory, but then, crucially, that star has to die.
It has to die a very violent death. It has to go supernova to disperse that newly forged oxygen out of its core and into the interstellar medium, the gas within the galaxy.
So finding a detectable amount of oxygen at redshift 6.71 tells us 2 things. First, that enough massive stars have already lived their short lives and died to create this heavy element.
Which implies there was already a rapid cycle of star formation happening even before this merger event we're seeing.
And second, and this seems like the more profound point, that oxygen isn't just staying neatly inside the galaxies where it was made.
No.
It's out in the void. It's in the space between the galaxies.
Exactly. This is direct visual evidence of the enrichment of what we call the circumgalactic medium, or the CGM, maybe even the intergalactic medium, the IGM. The big question then becomes, how did it get there?
My first thought is galactic winds. We see this in local starburst galaxies like M82, the Cigar Galaxy. The supernova rate is so high that the collective energy from all those explosions drives a superwind, basically blowing enriched gas out of the galactic plane.
And that is an excellent candidate, and it's almost certainly playing a role here. I mean, when you have a star formation rate of 250 solar masses per year, the amount of feedback you get from supernovae is just tremendous.
Yeah.
You are literally blowing the galaxy apart from the inside.
But the team's analysis suggests something else is happening here, either instead of that or maybe in addition to it.
In addition to it, the geometry of this halo, the way it seems to form bridges and streamers, points to another powerful mechanism at play.
Gravity again.
Tidal stripping.
Okay, walk us through that mechanism. How does that work?
So imagine just 2 galaxies passing close to each other. The gravity of galaxy A pulls on the near side of galaxy B more strongly than it pulls on the far side.
Right, a differential force.
Exactly. That's the tidal force. And it stretches galaxy B. It can rip these long streamers of gas and stars out of the main body of the galaxy. We call them tidal tails.
Like the beautiful long tails you see on the antenna galaxies or the mice galaxies.
The very same. Now take that concept. Instead of 2 galaxies in a graceful dance, imagine 5 galaxies in a chaotic mosh pit.
Yeah.
The tidal forces are chaotic. They're multi-directional. You're not just pulling tails. You are churning the gas.
Yeah.
You're ripping it out of the individual gravitational wells of these little galaxies and flinging it into the shared space between them.
It's a cosmic blender.
It is a cosmic blender. And this is so crucial because it shows us exactly how the universe gets seeded with heavy elements so very early on. We used to think that enrichment was a slow process, that galaxies sort of held onto their metals for a long time.
They kept them to themselves.
They did. But this shows that these violent merger events are incredibly efficient at, for lack of a better word, polluting the surrounding environment.
Polluting in the best possible way, though.
The absolute best way.
Because without that specific pollution, you don't get the building blocks for rocky planets. You don't get silicon, you don't get iron, you don't get the oxygen we're breathing, you don't get us.
Precisely. If that oxygen stays locked inside the stars, or even just inside the galaxy, then the vast spaces of the intergalactic medium remain pristine hydrogen and helium forever. But here we are, seeing the exact mechanism for spreading the seeds of life, or at least the seeds of chemical complexity, very, very early in the cosmic timeline.
I want to pivot now to the crisis aspect of this discovery. We see headlines like this all the time, Webb breaks cosmology, the Big Bang is wrong.
Yeah.
And I tend to roll my eyes at those because usually it's just a small refinement of some error bars. It's not a crisis.
It's usually hyperbole.
But Dr. Popovich, one of the lead authors, used some pretty strong language here. He explicitly talked about needing to update the textbooks.
He did. And he is not someone who is prone to hyperbole. He's a very careful scientist.
So what is it specifically about our standard model of cosmology lambda CDM that is threatened by this quintet? Is it the total mass, or is it just the timing?
It's the efficiency and the speed of assembly. Look, the lambda CDM model works incredibly well on the largest scales. It is spectacular. It predicts the cosmic microwave background, the large-scale structure of the universe, the distribution of dark matter halos. It's a triumph.
Man.
But when you zoom way in, down to the scales of individual galaxies, what we call baryonic physics, the physics of normal matter, like gas and stars, it gets a lot trickier.
Because there are so many feedback loops and messy processes.
So many. And the simulations that are based on lambda CDM typically predict that early galaxies are small and that their mergers are mostly pairwise. Galaxy A merges into Galaxy B.
Simple binary collision.
Right. To find a complex group of 5 pretty massive, intensely starbursting galaxies all merging at once, just 800 million years in, that suggests that structural formation can happen much faster and more explosively than our sort of vanilla simulations would predict.
So it's not that the underlying theory of gravity or dark matter is wrong.
Not at all. It just implies that the dark matter halos in certain very overdense regions of the early universe might have been collapsing or clustering far more aggressively than average.
It's like finding a fully built skyscraper in a city that's only supposed to be laying down the foundations.
That's a perfect analogy. Or maybe finding a construction crew that is working 24/7 with 3 shifts when you thought they only worked on weekends. It tells us that the Dark Ages didn't just end with a whimper. They ended with a bang.
The universe woke up and got straight to work. No waiting around.
Immediately.
This connects directly to something we talked about on the show a few months ago. Another JWST puzzle. The red monsters. These huge, quiescent, basically dead galaxies that Webb was finding at like redshift 3 or 4.
Yes, the impossibly massive, quenched galaxies.
Right. They were as big as the Milky Way, but they had already stopped forming stars completely. And the mystery was always, how do you grow that big and die that young?
That is the quenching problem in a nutshell. In the local universe, galaxies tend to die slowly. They just gradually run out of gas over billions of years. But to have a totally dead galaxy at redshift 3, a couple billion years after the Big Bang, you need to have formed all of its stars incredibly fast and then shut off the gas supply incredibly fast.
And JWST's Quintet, this feels like the prequel to that movie.
It is almost certainly the progenitor.
Yeah.
It has to be. Think about the math. Just follow the logic. First, you have a system that is actively merging 5 galaxies. That's how you rapidly build up the stellar mass required to become a monster galaxy.
Okay, check. That gets you the mass.
Second, you have a star formation rate of 250 solar masses per year. As we said, that is a completely unsustainable burn rate.
It's a cosmic gas guzzler.
It's the very definition of live fast, die young. There's a metric we use called the gas depletion time. It's simple. You just take the total mass of gas available for star formation and you divide it by the star formation rate.
So it tells you how long you have until the tank is empty.
Exactly. And when your denominator, the rate is that high, your depletion time just plummets. For this system, they estimate the gas will be used up or blown out in maybe 50 to 100 million years.
Which, in cosmic terms, is a blink of an eye. It's nothing.
It's instantaneous.
Oh.
So this quintet is going to fuse together. It's going to burn through all its available gas in one spectacular final fireworks show, and then silence. The star formation will quench. It'll turn into a massive red and dead elliptical galaxy.
And it'll do it by, what, redshift 6.5, maybe redshift 6, way earlier than we thought possible.
Exactly. So those impossible dead galaxies we found later on, at redshift 3 or 4, they finally have a plausible origin story.
They came from impossible mergers, like this one, happening even earlier.
It closes the loop. It actually makes the whole timeline consistent. You need these extreme, violent events like the quintet to explain the extreme dead galaxies we see a billion years later. If the early universe was all slow and steady, those red monsters just shouldn't exist. But because the early universe was apparently home to these chaotic mosh pits, it all makes perfect sense.
I love when the puzzle pieces click together like that. It's not that the entire model is broken. It's that we underestimated the variance. We underestimated the extremes at the edge of the bell curve.
And that's exactly what a deep survey like JD's is designed to give us: volume. When you survey a large enough patch of the sky deeply enough, you stop seeing just the average run-of-the-mill galaxies. You start catching the outliers.
And the outliers are what teach you about the limits of physics.
That's where the new discoveries are.
So let's talk about the future of this specific observation. The paper is out. It's published in a major journal. But the science isn't done right. They aren't finished with this data.
No, not by a long shot.
What's the next step for analyzing ELG 1 through 5 and their surrounding halo?
Kinematics. That is the next great frontier for this object.
Movement. You want to see how it's all moving.
Right now, we have a beautiful but static 2D picture. We know where the galaxies are in the sky, and we have a rough idea of their redshift, their distance. But what we really need to do is map the precise velocities of the gas and the stars within the system. We need to see if there are rotation curves or measure the velocity dispersion, how fast things are buzzing around randomly.
Why is that so important? Is it to weigh the whole thing?
It's to weigh the whole thing,
Yeah.
exactly. In astrophysics, mass is everything, but you can't put a galaxy on a scale.
Unfortunately not.
So you have to infer its mass by watching how fast other things are orbiting it. If the gas is whipping around at, say, 500 kilometers per second, you know there has to be a massive amount of gravity holding it all together.
And that gravity is coming mostly from
From the dark matter.
the invisible scaffolding that holds it all together.
Precisely. By carefully mapping the kinematics of this system, Dr. Hugh and his team can get a really solid estimate of the mass of the dark matter halo that's hosting this entire group. And that number is the critical input for the cosmological simulations.
So if the dark matter halo turns out to be way too big, way too early...
That is when you might start to sweat a little bit about the standard model. It puts real tension on how fast those structures can form.
Okay, so we're waiting to see just how heavy this thing really is.
Yes, and beyond just this one object, the goal is always statistics. If they found one quintet in this relatively small JD's survey field, what does that imply?
Does it mean there are thousands of them scattered across the entire sky?
That's the cosmic variance question. Did we just get incredibly lucky and point the telescope at the one weird freak show in the early universe?
Or is this actually common?
And if it is common, then that has profound implications for how the entire universe was reionized. These violent star-bursting mergers would be incredibly efficient at punching huge ionized holes in that neutral hydrogen fog we talked about earlier.
They wouldn't just be little pinpricks of light. They would be the engines that drove reionization.
They could be the primary drivers.
Yeah.
It paints a much more dynamic, much more violent picture of that whole era.
It really does. I want to circle back here for a moment to the listener's perspective. We've been throwing around a lot of terms, redshift, jade, CGM, enrichment. But if I'm driving to work right now or walking my dog and I look up at the blue sky, which is blue because of oxygen and nitrogen, by the way, why does this matter to me? Why should I care about 5 blobs of light colliding 13 billion years ago?
It matters because it's our genealogy. We often think of the early universe as this alien foreign place. It's so far away in space, so long ago in time, it feels disconnected from us. But the physics happening in that quintet, the creation of oxygen inside those massive stars, the spreading of that oxygen by those chaotic tidal tails, that is the direct, unbroken precursor to the chemistry of our own solar system.
We are literally made of that pollution.
We are star stuff, as the saying goes. But more than that, we are merger stuff. The oxygen that is in your lungs right now, the iron in your blood, the silicon in the ground beneath your feet. It didn't just appear. It was cooked in the cores of stars, and then it was violently thrown out into the void by events exactly like this one.
This quintet isn't just a picture. It's us watching the universe's industrial revolution.
That's a fantastic way to put it. It's the moment the universe started mass manufacturing the raw materials needed for complexity, for planets, for life.
And the most stunning part of this discovery is that it started doing it way, way earlier than we ever gave it credit for.
That is the key takeaway.
Yeah.
It means the potential for complex chemistry, and therefore the potential for complex planetary systems, starts much earlier in the cosmic story than we used to think.
You know, that leads to a pretty provocative final thought. We usually assume that things like life, or even just the formation of rocky planets, is a late universe phenomenon.
Right. That's the conventional wisdom. You need a few generations of stars to die to build up enough metallicity in the gas to form a solid rocky planet.
But if you have these massive violent enrichment events happening at just 800 million years, if you're slinging oxygen and silicon and iron around the cosmos that early, could the clock for habitability actually start much, much sooner than we imagine?
It's highly speculative, of course, but it's not impossible. If you can create these localized pockets of very high metallicity very early on, you could theoretically form rocky planets around some of the first population 2 stars. But the stage, the chemical stage for life, might have been set while the universe was still a toddler.
It kind of reframes the Fermi paradox a little bit, doesn't it? If the universe has been potentially ready for life for 13 billion years, not just, say, the last 8 or 9, well, where is everybody?
That is a very deep dive for another day.
A very deep dive indeed. Before we wrap up, I just want to give proper credit where it's due. Dr. Wida Hu, Dr. Casey Popovich, and the entire JWST collaboration. It is so easy to see these incredible images on social media and just scroll past them.
It is.
But the sheer amount of human ingenuity and engineering required to park a telescope 1 million miles from Earth, keep it colder than the surface of Pluto, and have it stare at a patch of utter darkness for days on end just to catch a handful of photons from the dawn of time.
It's a monumental human achievement. It really is.
And the analysis that follows, teasing out the faint signal of 5 interacting galaxies from all the noise, from all the foreground objects, it's just as impressive. It's detective work at the very edge of reality.
Absolutely.
So I think the big takeaway for today is this. The early universe was not a quiet, lonely, simple place. It was a construction site. It was messy, it was loud, it was violent, and it was churning out the very elements of life at an absolutely furious pace.
And we are only just now, with Webb, beginning to see it clearly for the first time.
That is a thrilling thought. We finally opened the door to that room, and it turns out it's incredibly crowded.
Indeed.
Thank you so much for breaking this all down with us. This cosmic car crash has definitely reshaped my view of the dawn of time.
My pleasure. It's always exciting to look back this far.
And to you listening, the next time you look up at a clear, dark night sky, just remember, it looks peaceful now, but you're really looking at the aftermath of a very, very chaotic beginning. We'll see you on the next deep dive. Stay curious.